Record now. Okay, our meeting has officially begun. So first of all, are there any questions from either Larry or Ruth?
No, not really.
Really? No? Oh gosh. Yeah, I mean, it could be anything related to content or how the classes run, due dates, anything like that. I mean, there's always some, a bit of confusion about things like discussion topic responses. If you look at and even when I try to explain it in my videos, it doesn't always get across that well. So, pretty much your general due date is Monday of each week by midnight Phoenix time. However, your interactive overview, now I probably shouldn't say this, but I'll confess that the interactive overview, it's not worth many points. If you're a few days late on that, I don't really deduct any points. However, for the discussion topic, it's really important to keep the discussion going and actually to initiate the discussion that students post their responses by Thursday, because if you wait too long, no one's going to read your response and no one will have a chance to reply to it, and that means your response really didn't contribute much to the discussion. So each day I deduct a fraction of the total value of the that assignment. So try to get that in. If something happens, if you have some kind of family emergency or health crisis or something that prevents you from posting by that day, just let me know in advance and I can take that into account. And everything else really is due on Mondays. So for this first week, I need to open my calendar just to know what day it is. So that would be the 10th of July, Phoenix time. Okay. All right. Anyway, I guess since there's no questions there, you can interrupt me at any moment. That's fine. I have some. So my plan is I have a few slides. I'm just going to talk a little bit about the history of the concept of the atom, the development of the idea of the atom, and work through the simulation. So I'll do my best without giving everything away to show you how to run the simulation and give you an idea of what I'm looking for when I grade your essays. Okay. So first, my short presentation here. So this is week one. We're talking about atoms in motion. As we understand, we're mostly talking about temperature this first week, at least with the simulation. And temperature can be understood as a consequence of mechanics, the motion of atoms. It's always a cart before the horse, or egg before the chicken kind of question, chicken and egg type of question. Is it heat that gives motion, or is it motion that gives heat? So heat, which we measure by temperature, is a measure of the average kinetic energy of molecules or atoms in a substance. So they're moving around and we make them move by contact. So you probably don't see me right now, or maybe you see me down in the corner of the image or whatever, but if you rub your hands together, they warm up. Or I've never had this really work for me, but the idea of sitting over a campfire and taking two sticks and rubbing them. Actually, I nearly did I did get myself in a bit of trouble in middle school because we had a display. I don't even remember the context. We were probably talking about ways people were tortured in colonial America, but we had a stocks set up, where they would put your head a couple of boards with some holes in them, put your head through it in your hands, and people would throw rotten apples at you and insult you and make your life general misery for a long time before they let you out. Anyway, we had that in there, and we also happened to have a little a bow and I don't know, a stick, and I found there was a little dip in the base of that stalk, the stalks that were set up there. And when the teacher was out, I don't know, I think it was before class began, like 5 minutes before class began. Being the, well, I was never really a troublemaker, but, sometimes I did things without thinking ahead enough. And I wanted to say intrepid, that's the word, being the intrepid student that I was. I took that stick and the bow, I twisted the stick and the bow so that when I made the bow go back and forth, the stick would turn. So I put that stick down in that recess in that wooden board and went back and forth, and it started smoking and got really hot. And Mr. Sink, my social studies teacher, was not amused by that one bit. But anyway, those were the good old days. And, nowadays a student, who knows, they might get expelled or something, but he just kind of glared at me and said, "Robert, don't ever do that again." What I was doing was I was moving two surfaces against each other very rapidly. And the molecules in the stick were actually, colliding as the stick moved back and forth. It was rotating, but those molecules were moving relative to each other and colliding. And I was doing work by moving that bow back and forth. So I was using this. This is going to become apparent later in later simulations when we would talk more about energy. But my body stores energy in chemical form and then converts that into mechanical energy, which is motion. And that motion caused collisions between atoms. So I was transferring my chemical energy into the kinetic energy of the molecules in the wood. And so those molecules were actually moving back and forth because they were bound in a solid. So think of a mass on a spring, jiggling back and forth. The rate at which it jiggles is basically a measure of temperature. So the faster it jiggles, the more temperature there is, the hotter it is, the more heat energy there is. So heat is understood as really mechanical motion on a microscopic or submicroscopic scale. So it's really one idea, the same idea that we use to describe balls rolling down inclined planes or rocks falling off of cliffs. All the stuff we know, all the stuff we use, the concepts we use to describe that can be applied to at the atomic or molecular level. But we don't feel, if somebody throws a baseball in my hand, I feel the impact. But if you have trillions, many trillions of tiny little particles constantly colliding with your hand, you don't feel that as collisions. Our body interprets those many collisions per second as heat. So you're feeling that motion, but you're not feeling it as you would normally feel motion of a macroscopic object. You're feeling it as heat. Okay. So anyway, I didn't even plan to talk about that, but I had some fond memories all of a sudden of Mr. Sink and his eyebrows raising when he came into the room and smelling the smoke. And that was before we had smoke detectors in classrooms and all that good stuff. All right. The origin of atomic theory, I guess you would say, can be traced back. At least the standard story goes, for all I know, there could have been people with similar ideas in China and outer Mongolia and what is now, Saudi Arabia, who knows, and down in Ethiopia, for example. But anyway, as far as the recorded conjectures about this, we can go back to Democritus more than 2,000 years ago. And he was a philosopher with a lot of followers, and he had a lot of interesting ideas, but one of them was the idea of atoms. And he suggested that the elements, now the Greeks had, in the Western world, we associate the birth of science with the ancient Greeks. Of course, their view of the natural world is quite different from what ours is. But of course, they didn't have microscopes or electron microscopes or Geiger counters or any of these things we use these days for analyzing matter. It was more philosophical. And they broke the universe down into 4 elements: earth, fire, water, and air. Earth, fire, water, and air. And if I remember right. And they believed, I mean, they had kind of a primitive idea of, well, what is the modern idea? That, basically everything is made up of a combination of atoms. We have over 100 different elements that we know about now. And I mean, most of the things we experience day to day is a relatively small subset of that 100 plus elements, because a lot of them are very heavy and some are radioactive and don't linger that long. But anyway, they believed that you could make up everything we experience out of these 4 elements. And these elements were made up of innumerable atoms, which each atom had the characteristics of that element. So you could break down fire into its fundamental parts and break it down no further, and that fundamental part had all the characteristics of fire, and the same for air, earth, and water. Okay, well, that of course is a far cry from how we understand it today, but still, in a sense, in a very broad sense, they were on the right track. So, I mean, basically, it was a huge leap philosophically to even consider that the world was made up of small particles rather than being continuous, right? I mean, even that in itself is a tremendous leap of conceptual leap. That's the word. That's the expression I want to say. It's a huge conceptual leap to go from an idea of continuous matter, where you could subdivide it infinitely, to an idea of discrete matter, where the smallest parts would be atoms. Well, that idea sat around for about 2,000 years and really went nowhere, as far as I know. Now, I'm not a historian of science, so you might find some insights along the way that I'm not even mentioning. And then we come, look at the huge time difference. I mean, it really is about 2,000 years from Democritus to John Dalton. John Dalton was a chemist, but, in those days, a lot of people were called natural philosophers or natural scientists. And there was not much distinction between a chemist and a physicist or a geologist. They were all kind of doing the same thing. So Dalton was a scientist, and he, by that time, they knew a lot more about how elements combine, like 2 parts hydrogen to 1 part oxygen make water. And you could say the same for carbon dioxide, right? 2 parts oxygen, 1 part carbon. They were doing experiments already by the 18th century that showed that you could take certain elements and combine them in well-defined ratios to create a new compound. So he thought that the idea of atoms, it made perfect sense. If you thought of hydrogen being made up of hydrogen atoms and oxygen being made up of oxygen atoms, then you would have 2 hydrogen atoms and 1 oxygen atom combining to make water. And that would explain why, if you combine oxygen and hydrogen in the ratio of 2 to 1, all of those gases would be consumed, and you would end up with a certain amount of water. And the mass of that water that you got out of that reaction was equal to the mass, the total mass of hydrogen and oxygen that you combine to make that water. So all these ideas hung together. That wasn't proof of atoms, but it was a good argument. And of course, Mendeleev, a bit later than John Dalton, made his periodic table, and that also pointed to the existence of atoms. But this idea was really just that, an idea that seemed to be convenient. But there were a lot of scientists prior to the 20th century, in fact, who doubted the actual reality of atoms. They thought of it just as a convenient conceptual, idea, but not something that's real. Then we come to, two very different figures that played a very important role in the acceptance of the existence of atoms. On the left, sort of a similar time period as Dalton, is Robert Brown. And Robert Brown was a botanist. So he studied plants, and he was examining pollen grains under a microscope. And I guess they were suspended in water. And he noticed that they moved in a very odd way, kind of a random motion. They call it a random walk, or a drunkard's walk. If you imagine someone who's a bit intoxicated, probably can't walk a straight line. It turns out that the distance, if they walk, randomly, each step is in a random direction, you can actually predict how far they'll walk after a certain number of steps. And that distance is actually proportional to the square root of the number of steps. In other words, if someone takes one step, let's say he goes a distance of 2 feet in one step. If he's walking randomly, on average, how far will he go after 100 steps? Well, it goes as a square root. So that would be 10. Square root of 100 is 10. 10 times 2 is 20. So you would expect the person to have gone a distance of about 20 feet from his original position, if he's truly making a random walk. Anyway, Robert Brown described this phenomenon. First, he thought that pollen grains were maybe alive, that they were, had flagella or something, and they were swimming around. But then he even put other, I think, tiny grains of minerals in solution, which he was sure they were not living matter, right? They were inanimate matter, and they moved in a similar way. So he ruled out the possibility that it was some kind of attribute of living organisms. It was something else, but they didn't really know what it was. And then this guy comes along on the right. Here he is at about the time he wrote the paper, at the age of 26, Albert Einstein, with his young family. And at the time, he was just a patent examiner in a patent office in Bern, Switzerland. And he had a lot of time on his hands, and he liked to think about things. And it turns out in 1905, like I said, at the age of 26, he wrote 3 totally revolutionary papers. One, just about anyone would associate, or at least the concept they would associate with him, and that was his paper on special relativity, where the famous formula E=mc² comes from. But that was just one of the 3. The other paper, he talked about the existence of photons, particles of light, and he basically is sort of the father of quantum mechanics, the science that now gives us our cell phones and these computers and everything. None of this, lasers, all these things would not exist if it weren't for quantum mechanics. And we can trace quantum mechanics, at least one major path goes back to Einstein. There are certainly other important people in quantum mechanics, but he's one of the most important ones. And he wrote that paper at that same year. And then he wrote this paper on Brownian motion. He suggested that Brownian motion was a result of innumerable collisions of tiny atoms or molecules with pollen grains. And this is a beautiful example, actually, of how science works. So he assumed that was the case. He said, let's assume atoms are real. So temperature is really just a measure of the kinetic energy of atoms, like I explained earlier. If that's so, we can make predictions about what happens when these atoms that carry a certain amount of kinetic energy collide in a random fashion, very rapidly with something much more massive than those atoms. These pollen grains were much, much more massive than atoms. We can see the pollen grains, even though they're tiny, but we couldn't see the atoms or the molecules. If that's true, he made a model, not a physical model, but a conceptual model of what's going on. He just pictured a big ball and a bunch of tiny little balls moving around randomly, and how fast they move was measured by the temperature. So he derived a formula that predicted how far, if these random collisions were really occurring between atoms and a pollen grain, he could calculate and predict how far that pollen grain would move in a certain amount of time. And that's his formula right here under the title, Atoms Are Real. So D is the distance the pollen grain moves. This symbol here is a square root. So he's taking the square root of everything in the brackets. K sub B is a constant. If you've ever had thermodynamics, which I'm sure most of you have not. Anyway, it's a very important constant called Boltzmann's constant. It's a very standard number in physics and chemistry. T is the temperature, and then divided by 6 times pi, 3.14. Eta here, this N-shaped letter is the Greek letter eta. That's a measure of the viscosity, because it does depend on the liquid it's in. If you were doing this Brownian motion measurement in water, you'd get a different result than if it was in honey, right? So viscosity, how thick that liquid is, how it resists motion, has an effect. And R is the size of the pollen grain, the radius of it, that we assume it's a spherical object. And T is the time in seconds, okay? So these are all pretty simple things to measure. Temperature, viscosity, radius. I mean, they could see the pollen grain under the microscope, so they could estimate the radius of the pollen grain, and obviously you could measure the time. So he generated a formula that predicted how far the pollen grain would move in a certain amount of time. And a French scientist shortly afterwards used this formula, had different pollen grains, different sizes, measured how far they moved in a certain amount of time, and confirmed Einstein's formula. Einstein's formula was based on the assumption that atoms are real, and the formula correctly predicted how far the pollen grains would move in a certain amount of time, given the known temperature, viscosity of the fluid, and the radius of the pollen grain. So we never say we prove anything in physics or science, but this was very strong evidence that atoms are real. Okay, the assumption was atoms are real. A prediction was made. Experiments confirmed that prediction. So you made a nice closed loop. And of course, once atoms were accepted, I mean, this was kind of the decision point. Once this prediction was made and the experimental confirmation of the prediction was done. And of course, people in other labs around the world did the same experiments and independently confirmed this. Then it was pretty much a closed case for atoms. People all of a sudden, said, okay, yeah, atoms must be real. And it's the acceptance of atoms that has made possible all sorts of developments in technology, the invention of the transistor, which some people might consider the most important technological innovation of the past century, because without the transistor, we wouldn't have computers and smartphones or any most of the things that make our lives different from the lives of people in Einstein's time, for example. Okay. Now, with Einstein he still treated atoms as just solid balls. He didn't even worry about their structure. It's not that he didn't think about the structure of atoms, but it wasn't necessary for his calculation. He was able to just treat them as tiny little marbles colliding with things. But experiments were performed later. You see here, the guy on the left is Ernest Rutherford. And in the early 1900s, he did an experiment where he took a thin film of gold. I mean, there's many other players in this. Another important player in this story is J.J. Thomson, who you can read about on your own. But he's the person who basically discovered the electron. And he did a beautiful experiment where he measured the ratio of the charge to the mass of the electron. He didn't know the charge of the electron or the mass, but he could divide the charge. His experiment told him what that ratio was, okay? And once another person by the name of Robert Millikan actually measured the charge directly of the electron, then they knew the mass, because if the charge to mass ratio is some number and you measure one of those numbers, you know what the other number is. Anyway, J.J. Thomson had a model which I'm trying to think what he called it. It was like the raisin bread model or something like that. But anyway, he imagined electrons which have negative charge and protons. Well, they didn't really know about protons, but he assumed, since matter is usually neutral in charge and electrons are negative, there must be positive charges also. So he imagined that matter was made up of electrons and some positive charged particle distributed kind of uniformly throughout the material. And Ernest Rutherford did an experiment to test this idea. And what he did was he took a thin film of golds, which was gold atoms, just a few layers of gold atoms. It was a very thin foil of gold. And he had a radioactive source that fired what are called alpha particles, which turn out to be the nuclei of helium, 2 protons, 2 neutrons. They didn't really know that at the time. They just knew that some radiation came out of this radioactive source. Anyway, he fired these particles at the gold foil, and based on J.J. Thomson's model with this kind of uniform distribution of positive and negative charges, he assumed that the alpha particles would just go through the foil and come out the other end. Like a bullet through tissue paper was his view of it. If you fired a bullet at tissue paper, the bullet would go straight through without surprising you, right? That'd be what you would expect. But it turned out that every so often the alpha particles would be reflected back in his direction. He had detectors that could detect it. You can't see it with your eyes, but you have detectors like Geiger counters, make a clicking sound every time a charged particle enters it. Anyway, he was very surprised by this. He said it was like firing a cannonball at tissue paper and having it bounce back at you. And he used that information to assume that there must be a very heavy nucleus at the center of the atom, which is positively charged, and electrons surrounding it. And that was a nice model. And then along from Denmark comes Niels Bohr on the right. And he was a young theoretical physicist. He was more interested in trying to understand, to get a conceptual understanding of things than doing experiments. Rutherford was experimentalist. Science is often kind of divided that way. Some people like to tinker with equipment and make measurements. Some people like to take those measurements and try to understand why they saw those results and then make predictions so that new measurements can be made. Anyway, Niels Bohr was a theorist primarily, and there were a lot of other facts about atoms that could not be explained by Rutherford's model. And again, it's a big story. It involves people like Max Planck and a school teacher by the name of Balmer. Actually, probably, I don't remember the dates, but probably about 50 years before these guys were doing anything. this German school teacher, Balmer, tried to understand why hydrogen emitted light in discrete colors. You know, if you make hydrogen gas glow like a neon bulb, you can do the same with hydrogen, a lot of gases, not just neon. It doesn't emit a continuous rainbow like we see from the sun. It emits discrete lines. There's just a few, 4 or 5 colors that it emits. And he tried to understand this. It was almost like notes on a guitar. There were certain frequencies, and there's ratios, numerical ratios between those frequencies that were hard to explain. Anyway, Niels Bohr said, if I assume electrons can only occupy certain orbits, not any orbit, in the solar system is not a perfect model for the atom because there's nothing preventing a planet from orbiting between Earth and Mars, or Earth and Venus, or Venus and Mercury. Okay, they could orbit anywhere at any distance from the sun. However, it turns out electrons can only orbit at certain distances from the nucleus. And once you assume that, then they can only emit certain energies if they change their orbit. If it drops from a higher orbit to a lower orbit, that energy has to go somewhere, and it's emitted in a form of light. And anyway, Niels Bohr then applied the idea of quantum theory to the atom to form the Bohr model of the atom. Okay, and that more or less, the atom has evolved even from that. It's a much more complicated picture, but in your usual chemistry text, the Bohr model is perfectly adequate for explaining most of the things we need to know to understand chemical reactions. So was that, and that gets us to more or less the modern model of the atom. So I just want to close here with a excerpt from a lecture or an interview with Richard Feynman, the author of our textbook. And I just remembered I made a mistake here. I'm going to have to reshare the screen because I didn't share the audio. So let me fix that real quick. But I'm going to have to stop sharing and then reshare. Okay, and I see that, let's see, looks like Brianna has joined us since I started. Welcome, Brianna. And I'm going to share the screen again and share the audio. Okay. So this is Richard Feynman talking about atoms and how he's basically saying in his own wonderful way what I was trying to say at the beginning, how we can understand heat in terms of motion. This is what scientists have been, this is where progress comes, when you can take one idea to explain many different, at one time, what seemed to be unrelated phenomena. So you take a lot of things that make the world seem very confusing, and you figure out a way to explain many different phenomena with one explanation, one model. And he calls that, in the textbook, he calls that conglomeration. Okay, you could call it unification, for example. Having one explanation for many different phenomena, which makes life a lot easier for a scientist or an engineer. Okay, so here he is talking about that. I hope you hear it. If you can't hear it, speak up and I'll try to do something to maybe make it audible. Okay, here we go.
Nothing's really as it seems. We're used to get, hot and cold, and all that. Hot and cold is speeds that the atoms are jiggling. If they jiggle more, it corresponds to hotter, and colder is jiggling less. So if you have a bunch of atoms, a cup of coffee or something sitting on a table, and the atoms are jiggling a great deal in the coffee, and they bounce against the cup, and the cup then gets shaken, and the atoms in the cup shake, and they bounce against the saucer, and the heat heats the cup, and heats everything else. That hot thing spreads its heat into other things by mere contact, because the atoms that are jiggling a lot in the hot thing shake the ones that are jiggling only a little bit in the cold thing, so that the hot heat, we say, goes into the cold thing, it spreads. But what's spreading is just jiggling and irregular motions, which is easy to kind of understand. It brings up another thing that's kind of curious. That I say that things jiggle, and if you're used to balls bouncing, you know they slow up and stop after a while. But we have to imagine with the atom a perfect elasticity. They never lose any energy. Every time they bounce, they keep on bouncing off, and they don't lose anything. They're perpetually moving. And that the things that happen when we say something loses energy, if the ball comes down and bounces, it shakes irregularly some of the atoms in the floor. And then when it comes up again, it leaves some of those atoms moving, jiggling. So as it bounces, it's passing its extra energy, its extra motion, to little patches on the floor each time it bounces, and loses a little each time, until it settles down, we say, as if all the motion has stopped. But what's left is the floor is shaking more than it was before, and the atoms in the ball are shaking more than they were before. At the organized motion of all these atoms moving the same way, falling down, and the quiet floor is now transformed into a ball sitting on the ground. But all that motion is still there in the form of the energy of motion, in the form of the jiggling of the floor, which is a little bit warmer. Unbelievable. But anybody who's hammered a great deal on something knows that it's true, that if you pound something and hit it a lot, you can feel the temperature difference. It heats up. It heats up simply because you're jiggling it.
Okay, so that's
a beautiful one.
That's what he was saying, that like if you have a super ball, a hard rubber ball that's bouncing, it doesn't bounce forever. Each time it bounces, it loses a little energy, but where does it go? It goes into, when the ball hits the floor, it makes atoms or molecules in the floor start to jiggle. And that energy that's contained in their jiggling is taken away from that bouncing ball. So that bouncing ball loses energy, but that energy is not really lost. It's just transformed into this randomly distributed energy in the floor, which we measure as heat. And as he also said, anyone who's pounded a nail knows that after you hit it a few times, the nail gets pretty hot. And that heat is just the amount of energy that you've converted. You're swinging that heavy hammer. There's a lot of energy there. When it stops on the nail, that energy doesn't disappear. It's converted into random motion in the nail. And that random motion we perceive as heat. We don't actually feel that jiggling as, little particles jiggling, because they're too small and the distance they move is too small for us to distinguish. But our senses interpret that as increase in temperature. All right. So
You can keep looking.
And that's an important concept, because prior to Einstein and this understanding now of what heat really is, people thought heat was some kind of fluid. That heat was actually a physical thing that you could move from one thing into another, but it's not a physical thing. It's a measure of motion. It's a measure of energy. Okay, and now I will pause for a second and take a breath. So, are there any questions from the audience? Oh, let's see. Oh, I guess Larry, I didn't see that at the end of his question. Explain how exactly atoms join. Well, I don't know if I can explain exactly how atoms join. It's a fairly complicated story, but let me see if I can open the whiteboard. How am I doing this? There it is. Okay, I'm trying to open the whiteboard here. It's kind of weird. Didn't open the way I expected. Okay, maybe this is going to work. All right. Let me get my stylus. I'm probably making a mistake by even trying this because I often have trouble with my stylus, but I'm going to give it a shot real quick because I don't have another way to illustrate this. But I think I put in the discussion a figure that showed masses connected by springs. Obviously, at the atomic level, you don't have springs. You have forces, electrostatic forces between atoms that play the role of springs. So the atoms are stuck together by these forces. Okay, so we know that atoms are made up of, protons and electrons going around them. Okay, going like that. There's some electrons, there's some protons in the center. Here's another atom. I'll just make it similar with some electrons. When they're close together, these protons attract these electrons. Okay, they're attracted to each other. So these atoms want to get together, but when they're too close, let's see if I can save myself some writing by using this lasso here. If the atom gets close, then these protons push apart. They don't attract each other anymore. They push apart. So really, this atom can only get so close before these positive charges, right, repel each other. So it kind of looks like this. Here's an atom out here. The nucleus, the positive charges. I'll put some plus charges here. Let me do this. So there's plus charges, and these are minus charges here. And you all know, right? Opposites attract when it comes to charge. Plus charges attract negative charges. So this atom would naturally want to, from a distance, it kind of sees the negative charge mostly, more than the positive charge. So it gets attracted. But when it gets too close, now these positive charges are pushing against each other. So the atom can't get any closer. Okay, it gets pushed away. So it's kind of stuck. If it's out here, it's attracted, and if it's over here, it's repelled. So it's kind of stuck in this region, and you can actually model this very well. It's actually, physically, it's not realistic, but in terms of actually describing what happens in atoms, bound atoms, it works very well. You can imagine atoms being joined by springs between them, right? And if the spring stretches, the atoms get pulled together. If the spring compresses, they get pushed apart. So basically, they're bound together. If you give this too much energy, so if you start hitting one of these atoms and heating it up, if you heat up the material, then this atom starts to jiggle back and forth, and at some point the spring breaks. Right, the spring will break, and now these atoms are moving more or less freely. I'm trying to do too much here. Okay, so now these atoms kind of move. If you add a lot of heat, that you break that bond between them, right? They get moved far enough apart that they're not attracted to each other anymore. And then the atom can kind of more or less move randomly around. And now you have If they stay more or less close together, you have a liquid. And if they're real far apart and basically don't feel the electric field from the other atom at all, it moves freely like in a gas, right? So that's the basic idea. If it's moving real freely far away so that this atom doesn't really feel the effect of the electrons in this atom, it's a gas. If it gets kind of close where they kind of interact, but they're not really bound together, you have a liquid. And when they get close enough where they're bound together, then you have a solid, okay? And that's why when you heat things and make them jiggle hard enough, you break that electric bond between them, you get a change of state. All right. That's my best I can do in my hand waving way to explain that. Okay. And now our understanding is good enough. You know, we can write actual formulas that will tell you at what temperature the transition would occur. You can predict for even new materials when that would occur. All right. Instead of having to actually do it, you can model it first, and then if it's like a promising material, then you can actually make that material. All right, now getting back to what I actually intended to do next, and this is what I'm going to wrap up with, our simulation. So pay attention, because a lot of students don't know how to follow directions, and this is your chance to actually see me explain the instructions. Okay, first of all, when you start the simulation here, you have an assignment guide. Click on that. Why did it say that? That's not what I expected. Let's try it again. Oh, there it goes. That was weird. Okay, sometimes you need to click more than once. You might notice it downloaded a file. If you don't see it here, this is how Chrome works for me. It shows me the downloaded file. It's a Word document. If you don't see that, then go to your downloads folder and you'll see it there, okay? These are the instructions. Follow these instructions. If you follow these instructions to the letter, it's hard not to get a good grade on this assignment. Now I just have to find out where I was here. Okay. I want to try to share the screen. Come on. There we go. All right. Visit the States of Matter basic simulation, then do the following steps. So there's the link for the simulation, so click on that. Now you have two options here. I've had students go right to the wrong option. I don't know why. Okay, select states. There it is, select states. Now don't always go by pictures, read words. Words are important, okay? Sometimes pictures could be misleading. So words take priority when it comes to instructions. From the Atoms and Molecules menu on the top right, select oxygen. See, right now it has neon. I select oxygen. Okay. We've done that. Select the solid button. Observe the atomic structure of oxygen as a solid. Note the reading on the thermometer near the top of the container. Okay, now, if you look at the picture, you're going to see that they selected water. I don't know why they use that picture, but don't do water. If you want to do water on your own, feel free to do that later. I actually encourage that. But for your lab report, for your essay, it's about oxygen. I'm looking for oxygen results. So you select oxygen, please. Click on solid. There it is. When it says to note a temperature, that means write it down, okay? So I clicked on oxygen. You know, in your essay, you would say something like, you know, I started the states of matter simulation. I selected states. I selected oxygen from the atoms and molecule menu here. I clicked on solid and I observed a temperature of, and I will not say the number, I'll leave it up to you, the temperature reading. Okay, so write that number down. This is in Kelvin. It also gives the temperature in Celsius. Actually, in physics, we prefer Kelvin. I encourage you to use Kelvin. I'm not going to mark off if you prefer Celsius. You might want to look at Celsius to get a sense of, maybe you're more familiar with Celsius, and you see right now that this temperature in Kelvin is a very low temperature, far below the freezing point of water, right? So there we are on that. Now select the liquid button. Of course, describe what you see also. Okay. We want to be both quantitative, in other words, give a temperature reading, and qualitative. Describe what you're seeing. What kind of motion? How is it distributed? So select the liquid button. Observe the atomic structure of oxygen as a liquid. Note the reading on the thermometer. In other words, give the temperature that you see there. Okay, so give me the temperature and tell me what you see happening here. Please keep in mind, we're only simulating. I never tried counting this, but maybe it looks like maybe 50 molecules or something. You know, even the tiniest sample of oxygen that you could see with your eye would have trillions upon trillions of oxygen molecules. So we're seeing a fairly small statistical sample. And if you know anything about statistics, when you take a small sample, you're not necessarily seeing something that's really representative of a large sample. Okay, so just keep that in mind, because you're not going to see liquid, you know, crowding over to one side of a container, for example. But if you only have a few molecules, that is possible. All right. So that's that, and it shouldn't be surprising. You're going to select gas. You're going to write down the reading and observe what's happening in this cylinder within this container. What are you observing? And then it says cool the container by clicking and holding the slider to cool. So I'm going to move the slider to cool and observe the lowest possible reading. So hold that there. You might have to hold it there for a couple minutes to see how low it can go. And when it reaches its lowest point, tell me what that lowest point is, and tell me what you see happening with these molecules. Okay, anyway, I'm going to stop there. I could go lower, but I don't want to, because I'm lazy and I don't want to do everything for you. Okay, then heat the container by clicking and holding the slider to heat. Right? See how easy all this is? But just tell me what you're doing. Like in your essay, say, I slid this slider to heat and this started happening. Okay? So describe what you see happening as you do that. And it also says, observe the highest reading and pay attention to the change in motion. So if you have the patience, you might want to hold this there for a while to see how high in temperature you can go. Is there a limit to the temperature at the high end? And is there a limit to the temperature at the low end? Does it go to 1 Kelvin? Does it go to 0 Kelvin? Does it go to minus 10 Kelvin? Is there a limit? And in both directions. All right, and that's it. Now, I just realized something that I neglected here. I normally be aware I will probably update these instructions because it's still a little vague. You can go over 350 words. I mean, it's possible to write a perfectly good essay in 350 words on this simulation, but it's not always easy. So if you want to go 500, 750 words, go ahead. I'm not going to penalize you for that. Okay, I don't think you can say anything meaningful in less than 260 though. And I do suggest, I'm going to, like I said, I'm going to add some information here to help guide you further. But if you just, basically I'm going to copy what's on the rubric here. So open the rubric and look at all the things that I'm grading for. So I'm looking for, I want you to describe what you did. Like I was saying, you know, if you would transcribe my word, what I said verbally into text and clean it up a bit, you would get a description of the procedure. I want the procedure in own words. Don't just copy it from the assignment guide, okay? Do it in your own words. Doesn't have to be very long. Describe what you observed. That means what temperature did you see? What did you see qualitatively happening with the molecules? While you were doing it, some questions should have come to mind. I'm going to grade you on whether or not you ask a question. So please, surely there's some question related to atomic motion or molecular motion that you can frame from what you do in this lab. So ask a question, because I'm going to grade. Part of 15% of your grade is based on you asking a pertinent question. So even if you think you know everything, go ahead and ask a question. You can even answer it yourself if you want. Discuss 2 specific ideas from the reading related to the observations. So prove to me that you read chapter 1 and relate some of the things that a couple of the things Feynman says to what you observe in the simulation. And make a general statement about what the simulation taught you about atomic motion. So you could say, from the simulation, I learned this about atomic motion, that when you increase temperature, blah, blah, blah happens. When you decrease temperature, something else happens. You know, something like that. A general statement, you know, a general lesson that you learned in your own words. Use of references. Certainly you should use your textbook as a reference. So give me a reference to your textbook. So you can get that from the various ways. You know, you can get it from the university library, or, you know, basically I want to see Feynman, 6 Easy Pieces, Basic Books, 2011, something like that. You know, enough information. Don't just give me a link. Give me some text so that if I print it out on paper and couldn't click on the link, I could at least look, I could go to the library or go online and find the book. Check your spelling and punctuation. It's not much of your grade. It's only 2% of your grade, so it doesn't hurt you too much. But if I see something misspelled, I'll probably take off a little bit from this, okay? And language, as long as you're right at the college level, then you're fine, okay? So just, again, use reasonable grammar. Don't talk like a 6-year-old, okay? I heard something, so I think there might be a comment or a question. I'm going to take a look here. Ruth, okay, Ruth, let's see. Is part of the concept how many electrons are in the outer shell? If there is a sharing possibility, atoms will join. Right, well, you know, you can have covalent bonding. That's when atoms are sharing electrons in the shells, and that's what, you know, why there's 2 hydrogens for every oxygen, because the hydrogen needs to get it wants to complete its shell. It only has 1 electron in its, well, I don't want to say outer shell. It only has 1 shell that's occupied, and has 1 electron in it. It wants to have 2 to fill that s orbital, and it borrows it from oxygen. So yeah, there's sharing going on. But again, it's basic electric. It's the electric forces that are going on there. Okay. I've actually gone past the hour, but I did say everything I wanted to say. Again, be on the lookout. I'm going to probably update this by tomorrow. I'm going to add a few more things, but basically what it's going to be is just copying what's in the rubric. So if you've done it already, you can always resubmit. If I've said something, if you've already submitted the assignment, I haven't checked to see how many submissions there have been, if any. If you submitted it and you heard me say something and you thought, oh, I left something out, you can resubmit it. And I always will grade the latest submission, okay, the most recent. Unless you tell me otherwise, I will grade the latest submission and I will ignore any earlier submissions. All right. And I usually don't grade, you know, the due date is Monday for this, so I'm not going to start grading until probably Tuesday. And I don't get through all the grading until maybe next Saturday, a week from this Saturday. So just be aware of that. All right. I'm starting to ramble a bit. So anything else? Any last minute questions before we say goodnight? Okay. I take that as a no. So at this point, I say goodnight to everyone. And thanks for attending. I'm recording this. And assuming I didn't screw anything up, I will post a link to this recording sometime tomorrow. So you can always, if you miss something, you can always watch it again. All right. Okay. Thank you very much. And good night, everyone. I hope to see some or all of you or more of you next week.